Welcome back to the Deep Dive. Today we're continuing our CSWIP 3.1 exam prep series.
That's right.
We're tackling some really key multi-choice questions. But look, it's not just about memorizing the answer.
No, absolutely not.
We want you to get the why behind them, so you're prepped not just for the test, but for the real job.
Exactly. That foundational knowledge, it's everything in welding, isn't it?
Yeah.
Connecting theory to what you actually do day to day, that's what makes a difference. So yeah, let's get into some of these core concepts.
Okay, sounds good. Let's kick things off with electrode classification. It's fundamental.
Crucial stuff.
So the first question asks, which of the following electrode types is classified to EN ISO 2560? And the options are A, E38 3R,
Okay.
B, E6013, C, E7018G, and D, E5133B.
Right. Good mix there.
So thinking about that specific standard, EN ISO 2560, the one that fits is option A, E38 3R.
That's the one. And understanding why is key here. EN ISO 2560, that's the European standard we're talking about, specifically for covered electrodes, for manual metal arc welding, MMA, and it's for non-alloy and fine-grain steels.
Okay.
These codes, they're not random. They pack in a lot of information. Like E38 3R, the E is simple enough.
Electrode.
Electrode, yeah. The 38, that tells you about the weld metal strength, minimum yield, tensile strength, basically how strong it is.
Important.
Very. Then the 3.3, that relates to impact toughness, usually at a specific low temperature, like say minus 30 Celsius. Crucial if it's used somewhere cold.
Right, for low temp application.
Exactly. And the R, that tells you the coating type. In this case, it's rutile.
So each part gives you specific performance data.
Precisely. It's like a spec sheet condensed into a few characters. An inspector needs to decode that instantly.
And it highlights the difference between standards, too, because those other options.
Ah, yes. Good point. Things like E6013 or E7018G. Those look familiar, but they're actually AWS classifications.
The American Welding Society standard.
Right. Different system entirely. Focuses on tensile strength in PSI, welding position, coating, different structure. You mix them up. You could specify the wrong electrode.
Yeah. Easy mistake to make on an international job if you're not careful.
Yeah.
So knowing your standards is critical.
Absolutely vital.
Okay, let's move to something really practical. Big infrastructure stuff. Pipelines.
Oh, yeah. Stovepipe welding. Classic application.
Exactly. Those huge overland pipelines. Specific challenges there. Speed, penetration, often working vertical down. So question 2. Which type of electrode is used for stovepipe welding for overland pipeline construction?
Okay.
Your options. A, rutile. B, cellulosic. C, high recovery rutile. Or D, acid rutile.
For that specific job.
For stovepipe, the answer you want is B, cellulosic.
Definitely cellulosic. They're kind of special for this kind of work, aren't they?
They really are. What makes them the go-to?
Well, a couple of things. First, massive penetration, really deep, which you absolutely need to get good root fusion, especially on those thick pipe walls, often in one pass.
Right, efficiency is key.
Totally. And the other big thing is the slag. It's very fast freezing.
Fast freezing, why does that matter so much?
Because when you're welding vertical down, gravity is working against you. A fluid slag would just run down.
Oh, I see.
But this fast freezing slag solidifies almost instantly behind the arc. It acts like a little shelf holding the molten metal in place.
So that's what enables that fast vertical down technique.
Exactly. It's designed for it. You get speed and penetration. Now, there is a trade-off,
The hydrogen content.
Yeah. Cellulosic electrodes do have higher hydrogen levels. That can be a risk for hydrogen cracking in some situations.
So how do they manage that on pipelines?
Well, the fast travel speeds help, and often subsequent passes help diffuse some of it out. Plus, the specific steels used are generally manageable. It's a known factor they control.
Unlike, say, a rutile electrode.
Right. Rutile electrodes typically have a more fluid slag, less penetration. Great for general fabrication, but just not suited for the demands of stovepipe welding. Different tool for a different job.
Makes sense. It really shows how engineered these consumables are for specific tasks.
Absolutely.
Okay, so we've got the electrode. Now let's think about the power source driving it. Another fundamental. Question 3. Which type of power source characteristic is normally used for manual welding?
The power source itself, yeah. Critical.
Options are A, constant voltage, B, flat characteristic, C, constant current, or D, a motor generator.
Okay. For manual welding, MMA, stick welding.
For manual welding, the characteristic we need is C, constant current. CC.
Constant current, yeah. And it's worth thinking about why that's so important for manual welding.
Because the welder is controlling the arc length by hand, right?
Yeah.
And that distance is never perfectly steady.
Exactly. Even the bad welders have tiny variations in how far the electrode tip is from the workpiece. Millimeter changes.
So what does constant current do?
It compensates. It maintains a relatively stable welding current despite those small changes in arc length, which cause voltage to fluctuate.
Ah, so the heat input stays consistent.
Pretty much. If the current jumped wildly every time your hand moved slightly, you'd lose control of the weld pool. You'd get inconsistent penetration, loads of spatter. It would be almost impossible to produce a good weld.
So the CC machine gives the welder that stability they need to manage the arc manually.
Precisely. It allows for the human element, the skill, without fighting the machine. Now, that's different from...
Constant voltage.
Right. Constant voltage, or CV, sometimes called a flat characteristic. Option B there. That's typically for wire-fed processes, MIG, MAG, flux cord.
Where the machine controls the wire feed speed.
Exactly. The machine maintains the voltage, and the current adjusts based on the wire feed speed. Different process, different needs. For stick welding, CC is the standard.
Got it. Constant current for manual. Makes perfect sense. Okay, next question. Let's talk about something that could really frustrate welders, especially when using DC, an invisible force.
I think I know where you're going with this one.
Question 4. Deflection of the arc by magnetic forces that can make welding difficult to control is commonly known as what?
That magnetic menace.
Your options.
Hey.
Arc initiation, B, arc misalignment, C, arc blow, or D, arc constriction.
Okay. That phenomenon.
The deflection caused by magnetism. That's C, arc blow.
Arc glow. Yeah, it can be a real pain. It's basically the arc getting pushed or pulled off course.
By magnetic fields in the workpiece.
Exactly. It happens primarily with direct current DC, because DC sets up a steady magnetic field around the path of the current flow in the material being welded.
And sometimes that field isn't balanced.
Right. It can get concentrated or distorted, maybe near the ends of a plate, or if the ground clamp is poorly positioned, or when welding into corners. That imbalance creates forces that literally push the arc around.
And the result for the welder?
Difficulty controlling where the arc actually goes. It can become erratic, unstable.
Leading to defects, I imagine.
Oh, absolutely. Increased spatter is common, but also more serious things like lack of fusion because the heat isn't going where it should. Porosity, inconsistent bead shape. An inspector would look for those signs.
So how do welders deal with them?
Well, sometimes switching to AC current helps, as the alternating current disrupts those steady magnetic fields. Or they might change the ground clamp position, sometimes using 2 grounds. Maybe change the angle of the electrode, or even use shorter arc lengths. Preheating can sometimes reduce it too.
It's fascinating how these unseen forces play such a big role.
It really is. Welding is definitely a mix of physics and skill.
Okay, one final question for this session. Let's focus on a really critical weld quality parameter, penetration.
The depth of fusion.
Okay.
Hugely important.
In MMA welding, penetration is principally controlled by which of these? A, arc voltage, B, welding speed, C, ferrosilicon in the electrode coating, or D, current.
Principally controlled by, that's the key phrase there.
Right. Lots of things influence it, but what's the main driver? The answer is D, current.
Current, amperage. That's your main control knob for penetration depth.
Why is current the dominant factor?
Because current is directly related to the amount of heat being generated at the arc. More current means more electrons flowing, which means more energy being released, more intense heat.
And more heat melts more metal.
Exactly. Higher current equals higher heat input, which drives the melting deeper into the base material. It's a pretty direct relationship.
But what about the others? Like voltage or travel speed, don't they matter?
Oh, they definitely matter. They influence it, for sure, but not as principally as current. Arc voltage affects the arc length and the width or spread of the arc, which influences the bead shape and how heat is distributed.
Okay.
Welding speed dictates how long the heat source stays in one place. Go too fast, even with high current, and the heat doesn't have time to penetrate deeply. So speed affects heat input per unit length.
Right, I see the distinction.
But it's the current that fundamentally determines how much heat is available to do the melting in the first place. And things like ferrosilicon, option C, that's more about deoxidizing the weld pool and affecting the final mechanical properties or arc stability. It doesn't directly control penetration depth like current does.
So current sets the potential for penetration, and other factors like speed and voltage modify how that potential is realized.
That's a really good way to put it. Current is the primary control. Understanding that is absolutely fundamental for both welders and inspectors.
Well, that wraps up our questions for this deep dive. We've covered quite a bit EN versus AWS classifications.
Cellulosic electrodes for stovepipe.
Constant current power sources for MMA. That pesky arc blow.
Yep.
And finally, the crucial role of current in controlling penetration. Hopefully, walking through these has helped solidify not just the answers, but the reasons behind them.
Yeah, the goal is always deeper understanding, not just rote memorization. Thinking critically about why things work the way they do.
Yeah.
That's the knowledge that sticks with you and helps you solve problems out in the field long after the exam is done.
Absolutely. Well, thanks for joining us again for this part of the CSWIP 3.1 exam prep series. We hope it's been valuable for your studies.
Keep digging into those principles.
We'll be back with more soon. And maybe think about this as you study. How might newer technologies or materials start to change or challenge some of these fundamental welding principles we've discussed today? There's always something new on the horizon in welding.
Always evolving. Good thought to end on.